It's only theory. Problem solving we will do in heat exchanger design. Or should we combine this with heat exchanger design? That would be fantastic. Yes. So we'll do one thing. Okay. We'll not go to radiation. We'll first go to heat exchanger design. We'll complete it, and then we will go to radiation. Radiation would be the last because convection and heat exchanger design are combined, are interrelated. Okay. So let us do that first. Finish heat exchanger design. Yes. Tell me. Okay. Finish heat. Yeah, yeah. You can see that. So we'll see that. Okay. Chalo. Next. Now here, uh, since I have told you what is temperature profile does not change. The shape of the temperature profile. It does not mean temperature does not change. What does not change? Shape of the temperature profile. Temperature does change. Okay, temperature does change. How does it change? T mean actually mean temperature. Okay, the variation given as T mean is equal to, see, we know, see, what do we know? We know that dt by dx or dou t by dou x or dou t mean or dt mean by dx, dt mean by dx is equal to q dot w, that is constant heat flux, into p, that is perimeter, divided by m dot cp, right? This we have already know, is it not? So integrating we obtain Tm is equal to q dot wp divided by m dot cp x plus c1 at x is equal to 0. Tm is equal to ti, correct? Tm is equal to ti. Therefore, Tm is equal to ti plus q dot w p divided by m dot cp. Make sense? Clear? So you can know the T mean at any point of time if we know the heat flux. We know the m dot cp. We know what is p, perimeter. We can always calculate into x, of course. Make sense? So you can calculate what is T mean, is it not? Very important. What's the number? We have lost numbers. Yeah, we have lost numbers. Okay. So this is very, very important. Very, very important. Next, we will see wall temperature is constant. Next case. Done. Okay. Now next. No, not done. Right. After this is done, I'm going directly to free convection. After free convection is done, we will go to heat exchanger design. Then we will go as a last part. We will go to uh, So within 3-4 days we are completing convection.
So in this equation, Tm equal to dw.
Who said that?
Because dTm by dx equal to dTw by t.
Yes.
Put it in the same
No.
for dw.
No. Why not? The boundary condition is different. Correct? Yeah. So what will happen? This would be Tm. Here, constant of Tm would be, there is nothing called Tm here. We cannot do Tm at all. It is the T of the wall only. Wall at a starting and starting process. Behavior is the same. This is what is the importance of differential equations, right? One equation gives a family of curves, and you point, that is called general solution. Particular solution is based on the boundary conditions. General solution is a family of curve. What is a family of curve? What is the general solution for? What is the differential equation for circle?
2x
What is the differential equation for a circle?
plus dy by
Yeah, on the center, what is the thing? The center is on the origin. Then, if the center is on the origin, then what is the differential equation for a circle? You have to write only the equation x square plus y square is equal to r square, which is constant. So you differentiate 2x dx plus 2y dy is equal to 0. So here this 2 cancels. Dy by dx is equal to minus x by. This is the differential equation for a circle. Now what is, now when you say differential equation for circle, you can get all the family of circles. How do you set which is the family which is required, which is the solution, based on the initial conditions? Okay, at or initial or the boundary conditions. Understand? At x is equal to 0, y is equal to 0. You see, then it is 0. At x is equal to 1, y is equal to 0. You put. Then it's like, so that is the condition. Make sense? Okay. Check. Sometimes differential equations become very, very, very important. Okay. See, without differential equation also you can do this. Before the knowledge also, you can do this. You understood that. You know how to integrate. But then the importance of differential equation has to be understood. Then you'll appreciate this better. See, getting the answer is different, and appreciating it is indifferent. Why appreciating is important? Because you will get the solutions faster. You get an intuitive understanding. You don't wander around in calculations if your intuitive understanding is proper. You know which direction to do the calculation. Calculation anybody can do. Which direction to do the calculation. How we have to approach the problem. That is important. Okay, so next. Next one, let us go with constant surface temperature. Constant surface temperature. Tw is equal to constant or constant wall temperature. This is also we can say constant surface or wall temperature. So here what is happening is you have the duct with this being the x direction. Right. Now this would be the T wall which is constant. T wall is constant. And then what will happen? Initial difference will be very high. Later on, it will go lower and lower and lower and lower, right? And this last at the end, there will be some delta. And this last one is called delta T at the exit. And this can be delta T at the inlet. This is. delta T at the end. Finished? Correct. So this is length Li or L of the plate. Is it not? L of the plate. Let us say from 0 to L. Correct. So here what you have? You have T exit here. This is T exit. Okay. Delta T exit is done, but that is T exit. We know that. And notice this. This is T mean variation. And this is T wall, which is equal to constant. Correct. Now what should happen here? M dot, or if I write Q dot is equal to H A of the wall into delta T average. What is that? We can write this as H into A of the wall into T wall minus Tm average. We do not know what that average is. We'll check it out. Okay. So now, uh, the question is how to take the average. Is it not? Okay. How to take the average? Okay. Now, delta T average, delta T average can be evaluated, can be evaluated using using arithmetic arithmetic mean temperature difference, mean temperature difference called AMTD, or logarithmic mean temperature difference, which is called LMTD. Both can be arithmetic mean temperature difference or logarithmic mean temperature difference, or LMTD. What is arithmetic mean temperature? Let us see. Arithmetic mean temperature AMTD, which is can be written as, or if average T average delta T average is almost equal to, its approximate, keep in mind it's approximate. If I write delta T arithmetic mean instead of average, arithmetic mean, this can be written as delta Ti plus delta Te divided by 2, which can also be written as Tw minus Ti plus Tw minus Te divided by 2, which can further be written as Tw plus or minus Tw minus Ti plus Te divided. This is actually equal to, this is actually equal to T delta T arithmetic mean is equal to Tw minus Tb, where Tb is the bulk mean temperature. Bulk mean fluid temperature. This is the arithmetic mean, which is not, it's approximate, it is not actual. It does almost a calculation, because arithmetic mean assumes that the temperature difference is straight between these two. Only then you can take the arithmetic mean, is it not? Arithmetic mean assumes the temperature profile is linear, which is not the case, which can be taken for a short, small tubes, not for long tubes, is it not? For short tubes, it can be considered almost, the errors will be less. When it's a long tube, you have to take logarithmic mean. Let us look at what is logarithmic mean. Okay. So LMTD, AMTD, this is what is used in heat exchangers. Very important.
So how delta Ti is T1 minus T1?
Hmm?
Delta Ti is T1 minus T1.
T bar, T wall minus Ti, is it not? That is delta Ti. T wall minus Ti. Ti is here. This is T wall, Ti. That is delta Ti. Delta Te is T wall minus Te.
This is through duct only.
Duct only. Everything through duct. We are talking about internal flows only. Duct flows only. So we are in internal flows only. Doubts? Take time to understand. Okay. Yeah, collaborator, I think. But understand. Done. Agoita. Done. Oh, next. Now we know it is not proper. Okay, it assumes linear variation. Not proper. I will not want me to write that thing. Go on, right? Ah, I'll write. AMTD assumes linear variation. Linear variation of mean temperature. Mean temperature. Linear variation of mean temperature along the pipe. Right. This may this may this may give acceptable results. The acceptable we are talking about, not accurate. Acceptable results in some cases, but in most of the cases errors are unacceptable. Most of the cases errors are unacceptable. So we have to go with others. Okay. So let us see how to get LMT. Okay. Now let us derive LMT. Okay. So what we can do is instead of this, we can consider if you consider this figure again. So we need better one. Okay. So that I'll leave it there only. So here. When you consider LMTD or anything here, so what is happening here? The same thing what we have considered yesterday. Let us consider a small fluid substance here. Okay. Here what is going in is m dot Cp into Tm. and what is going out is m dot Cp Tm plus delta Tm or Tm minus delta Tm or anything dTm. dTm. I'll write Tm plus dTm. And there is heat which is going in here, which I will say dq, and this is dx. Let me say. Fine. If I use this, then what happens? M dot Cp, referring to the figure, referring to the figure, we can write, right along with me, students. Okay, we can write m dot Cp into dTm is equal to h into T wall minus T mean into dA of the wall. Correct. Now, since dAw is equal to P into dx, dAw is equal to P into dx, we can write dAw is equal to P into dx, and dt mean is equal to minus of d of T wall minus T wall minus T wall minus T mean. Correct. I can write this. I'm just adding a constant here. No, it's just mathematical DTM. We have DTM. Can we write it as a TW minus TM? Yes, of course. Because when you differentiate, you're getting DTM. It's mathematical. Don't think in terms of physical thing. Physical thing also it means, but more better mathematics. Fine. Now substituting it here, what we'll get is we'll get, therefore substituting, since this one we can write m dot Cp into minus of d of Tw minus Tm is equal to h into Tw minus Tm into dAw, which is equal to P into dx. Correct? No? Now we have to integrate, that's it. Okay. So we can write d of Tw minus Tm divided by Tw minus Tm is equal to minus of Hp divided by m dot Cp minus of m dot Cp. This is very, very important, students. Important equation. Important equation. Let us integrate that. Okay. Now let us do one thing. Arbitrary, shall I put this as 51 equation so that we will get it? Arbitrary, I'll put 51. So the previous one will go previous one. Okay. I forgot to put the equations here. So arbitrary, I'll put 51 equation number to this. Okay. So that the backside equation will go negative. Okay. I don't know what is the number. Okay. Arbitrary. Arbitrary, I'm doing that. Okay. So I need to refer to this or it's done. It's okay. I'll say arbitrary 51. Okay. A51. I'll write A51. Arbitrary 51. A51. Arbitrary 51. Okay. This is very, very important. Okay. Now we have to integrate. That's it, right?
Sir, dx is one.
It is d Tw minus Tm. I took this down. Tw minus Tm is already there here.
Sir,
I took that down. This I took it down. This minus I took it the other way. Yeah, because Tm is a Tw is a constant. Mathematical. You differentiate this, you'll get this. Otherwise, this minus will not cancel. I want to match with this. You differentiate this, you see. D of Tw is 0. Because otherwise there is a minus here. This minus and minus should cancel and give the dTm, is it not? ಹಾ ಶೈಲೇಶ ಒಂದು ನಿಮಿಷ ಆನ್ ಮಾಡ್ತೇನೆ. Yes, Shailesh, any doubts?
dx is there, sir.
Where dx? Yeah, dx comes here. dAw is what? 3 into dx.
HP.
HP. ಸಾರಿ, ಅದು ಡಿ ಎಕ್ಸ್ ನಿಮಗೆ ಮಿಸ್ ಆಗ್ತಾ ಇತ್ತಾ? ಇಲ್ಲ ಅಲ್ಲ, ಅದು ಕ್ವಶನ್ ಅಲ್ಲ ಅದು ನಿಮ್ದು. Honest. I like honesty. Any teacher will like honesty. ಏನು ಮಾಡಲಿಲ್ಲ? ಇಲ್ಲ ಸರ್ ಮಾಡಲಿಲ್ಲ, ಸಾರಿ. ಆಯ್ತು, ಸಾರಿ ಹೇಳಿದ್ರೆ ಆಯ್ತು. ಮಾಡ್ಬೇಕಿತ್ತು, ಹೌದು ಸರ್ ಮಾಡ್ಬೇಕಿತ್ತು. ಮಾಡಲಿಲ್ಲ, ಇಲ್ಲ ಮಾಡಲಿಲ್ಲ. ಏನು ಮಾತಾಡಲಿ ಅಂತಾನೆ ಮತ್ತೆ. Can you talk anything back? ಮಾಡ್ಬೇಕಿತ್ತ? ಹೌದು ಸರ್. ಮಾಡಲಿಲ್ಲ ನೀವು? ಹೌದು ಸರ್. ಯಾಕೆ ಮಾಡಲಿಲ್ಲ? ಆಗಲಿಲ್ಲ ಸರ್. ಮಾಡ್ಲಿಕ್ಕಾಗಲಿಲ್ಲ. ಆಗಿಲ್ಲ ಆದರೆ ಪನಿಷ್ಮೆಂಟ್ ತಗೋಬೇಕು. ಆಯ್ತು. Wall temperature I am considering constant. Obviously. Wall temperature is greater when we consider only then this is graph is there, is it not? If I put other way around, it will be down coming like this. HA delta T is Tm Tw minus Ti. T mean.
Higher minus lower.
Ah, exactly.
Why you are writing here? Higher minus lower only. Why are you putting minus?
Where here minus sign. Differentiation. Do differentiation. ಕರೆಕ್ಟಾ? ಅದಕ್ಕೇನು ಇದೆಯಲ್ಲ ಡಿಫ್ರೆನ್ಸಿಯೇಷನ್ ಇಲ್ಲಿ ಮೈನಸ್ ಟಿ ಎಂ ಬರ್ತಾ ಇದೆಯಲ್ಲ, ಅದಕ್ಕೆ ಮೈನಸ್ಗೆ ಇದು ಮೈನಸ್ ಕ್ಯಾನ್ಸಲ್ ಆಗಿ ಪ್ಲಸ್ ಬಿಡಬೇಕಲ್ಲ ಅಷ್ಟೇ. ಮ್ಯಾಥಮೆಟಿಕಲ್ ಅಷ್ಟೇ. ಇಟ್ಸ್ ಗುಡ್ ದಟ್ ಇಫ್ ಯು ಗೆಟ್ ಸ್ಟಕ್ ಇನ್ ಸ್ಮಾಲ್ ಥಿಂಗ್ಸ್. ಚಲೋ ಡನ್, ಈಸಿ. ನೆಕ್ಸ್ಟ್ ಬರ್ದಾಯ್ತಾ? ಈಗ integrating the above equation. Integrating the above equation, we obtain log of Tw minus T exit. How did I write T exit? Because I am putting the boundary conditions. Ts minus, I am integrating the above equation from inlet to exit. Only then you will get it. You will get log of T wall minus Te divided by T wall minus Ti, which is equal to minus HA H into P into L, HPL, not IPL, HPL, okay, M dot into C. Makes sense? What is that? This is area, area of the surface, area of the wall, total area of the wall, right? So what you can write, log of Tw minus Te divided by Tw minus Ti is equal to minus of HP H of A surface or A wall divided by M dot C. This we are going to use in heat exchanger design. Okay. Or I can say Tw or Tw minus Te divided by Tw plus minus Ti is equal to exponential e power minus of HA wall divided by M dot C. This will lead again to T exit can be equal to T wall minus T wall minus Ti into exponential of minus HAW divided by M dot Cp. So this is LMTD, okay? This is LMTD. This is temperature difference. Log mean temperature difference. Okay. We will write LMTD while waiting. We will write LMTD. Make sure this is important. Very, very, very important. Arbitrary 52. Arbitrary equation 52.
So that logarithmic profile of from Ti to T is
See there.
experimental.
Exponential. It's experimental as well as we have done is analytical, is it not? This is analytical. We have not assumed anything.
Yeah, just like
Yeah, graph is coming like that only because that's how the variation is, logarithmic variation.
from
After this,
getting
so
the
this
equation
we can write that. Okay, we can write that. After getting this is logarithmic. You see, TE is logarithm. Exponentially, it is coming nearby. We have arbitrary put it, then now we know it's exponential. After this, we know it's exponential. So exponentially approaches, which is realistic. It is our first guess, is it not? It will never reach T wall. However big the this is cube is, there will be always a difference. So can the difference be met? Never. Can never be met. If it is met, it violates the it violates which law? Second law of thermodynamics. Does it violate?
What's the second?
Huh?
What is
Will it reach the T wall? Will the mean temperature reach T wall at any point of time? If it's infinite, only when it's infinite it reaches. Otherwise, it never reaches. There's always a difference between wall and this. Okay, chalo. Next. Next one is let us look at um, yeah. So what happens here? So m dot cp m dot cp is actually what? M dot cp is equal to h a wall divided by log of T wall minus Te divided by T wall minus Ti. Correct. Now, substituting this in, see, m dot Cp is there. Okay. Now, m dot Cp, if you consider into the, okay. Now we know that Q dot, since Q dot is equal to m dot Cp into Te minus Ti, correct? Yes or no? That is the amount of heat which has gone into it, is it not? I'll give you time. Tell me, is this right or wrong? Correct? Now substituting, say this is arbitrary 53, substituting arbitrary 53 in the above equation, we obtain we obtain we obtain that m dot cp. In that equation we obtain, we can write here m dot cp. I can write this as q dot is equal to m dot cp. Instead of m dot cp we'll write h into aw divided by log of log of tw minus te divided by tw minus ti into te minus ti. Now this can be written as equal to, this can be q dot is equal to h a wall into delta t log mean, where delta t log mean is equal to te minus sorry, delta t log mean can be, there is a minus here, I'm very sorry, yes, there is a minus which I missed here, so there is a minus here, so you can write here ti, is there a minus there, m dot cp, there is a minus there, is it not? So that minus in m dot cp has to come, m dot cp there is a minus, okay, that minus has to be coming, okay, so that minus, because of which you will get this as ti t inlet minus t exit divided by log of t wall minus t exit, which is always less than 1, less, very less, compared to t wall minus ti. You understand? This is LMTD, very important. This is what is called LMTD, log mean temperature difference. Right? This is arbitrary 54, or let this be arbitrary 54, and let this be arbitrary 55, A55. Done. So this is very, very, very important. This is log mean temperature difference. Log mean temperature difference. Important, easy, nice. This is what happens in flows. Now let us look at Nusselt number. Okay, take some time here.
Here the whole thing is log mean temperature.
Which one? Delta TLM is log mean temperature. This whole thing is log mean temperature.
T minus
Ti minus Te divided by log of, that is log mean temperature. ಸರಿಯಾ ಆಯ್ತಾ?
So ಇದು T greater than TI.
ಇಲ್ಲ, ಇದು ಏನಾಗ್ತದೆ ಇಲ್ಲಿ? ಸಿ ಒಬ್ಸರ್ವ್ ಹಿಯರ್ ಸ್ಟೂಡೆಂಟ್ಸ್. TI is greater than TE. TE greater than TI. So what you will get? You will get minus. But here also TW minus TE is lesser than TW minus TI. So you get a negative here which cancels. So LMTD becomes positive. Log of a fractional number is negative, is it not? This is a fractional number, observe. So it comes negative. This negative cancels. So LMTD in general comes as positive. Good observation. Clear? Take some time. Take some time. Understand, because you may ask questions if you do it properly.
Because the both hot liquid and cold liquid.
Anything, yes, cold liquid and hot. Anything is possible. We will look at this more into the depth in heat exchangers, which we are going to do. Now I'm going to talk about Nusselt number, and after the Nusselt number, directly I'll go to the natural convection. Once natural convection is completed, I'll go with heat exchanger design. There are questions on natural convection. One more class on natural convection and pipe convection problems, which has come in gate. Once that is done, we'll go with what? Heat transfer. Oh, sorry, we'll go with heat exchangers. Heat exchangers may be, so what is the date today? 25th, is it not? Heat exchangers I will start on Saturday. Okay, so 25th, tomorrow evening class I am completing natural convection as well as problems. Tomorrow morning class is not there. Natural convection I'll start in a moment. In another 10-15 minutes I'll start natural convection. Okay, so 26th I'm going to start with ಏನಾಯ್ತು ಫಾಸ್ಟ್ ಆಯ್ತಾ? ಕ್ಲಿಯರ್ ಉಂಟಲ್ಲ? ಆಯ್ತಾ? 26th ಗೆ ನಾನು ಇದು ಯಾವುದು ನಿಮ್ಮ ಹೀಟ್ ಎಕ್ಸ್ಚೇಂಜರ್ ಶುರು ಮಾಡ್ತೇನೆ. 26, 27, 28 ಮೇ ಬಿ ಹೀಟ್ ಎಕ್ಸ್ಚೇಂಜರ್ ಕಂಪ್ಲೀಟ್ ಆಗ್ತದೆ along with problems. 29, 30 I have to take more class. Sunday I'll take more classes. Sunday 4 hours I will take class. 4 hours will be our ಏನಾಯ್ತು ಹೇಳಿ? ಫಾಸ್ಟ್ ಆಯ್ತಾ, ಸ್ಲೋ ಆಯ್ತಾ, ಕರೆಕ್ಟ್ ಉಂಟಾ, ಬೇಗ ಆಯ್ತಾ, ಸರಿ ಆಯ್ತಾ? ಸರಿ, ಓಕೆ. ಏನಾದರೂ ಇದು ಆಯ್ತಾ? ಸೊ ಏನಾಗುತ್ತೆ, ಇದಾದ ಕೂಡಲೇ ನೆಕ್ಸ್ಟ್ ಏನು ಮಾಡೋದು ನಾನು? ಸಂಡೇ ನಿಮ್ಮದು 4 hours ನಮ್ಮ ಮುರಳಿ ಬೋಧ ಕ್ಲಾಸ್ ಇರ್ತದೆ. 4 hours ನಂದು ಕ್ಲಾಸ್ ಇರ್ತದೆ. 8 ಗಂಟೆ ಕ್ಲಾಸ್ ಇರ್ತದೆ. ಆಯ್ತಾ? ಪರವಾಗಿಲ್ಲ ತಾನೆ? ಏನಾಯ್ತು, ಎಂತ ಉಂಟು ಸಂಡೇ? ಮಾಡ್ತಾ ಸರ್ ಸಂಡೇ ಸಂಜೆ ಒಳಗೆ ಮುಗಿಸ್ಬೇಕು. ಏನಾದ್ರು ಪ್ರಾಬ್ಲಮ್ ಇದು ಉಂಟಾ, ಪ್ರೋಗ್ರಾಮ್ ಉಂಟು ನಿಮಗೆ? ಸರಿ, ಪರವಾಗಿಲ್ಲ, ಹಾಗೇನು ಆ ಥರ ಏನಿಲ್ಲ. ನಾವು ವಿ ಆರ್ ಆಲ್ಮೋಸ್ಟ್ ಕಂಪ್ಲೀಟೆಡ್ ದ ಸಿಲೆಬಸ್, ನೋ ಪ್ರಾಬ್ಲಮ್ ವಿತ್. ಸೊ ಡೋಂಟ್ ವರಿ. ಓಕೆ, ಸಂಡೇ ತಗೋಬೇಡಿ ಅಂತ ಹೇಳಿದ್ರೆ ನಾನು ತಗೊಳ್ಳಲ್ಲ, ಆಯ್ತಾ? ಏನು ಪರವಾಗಿಲ್ಲ, ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಅಷ್ಟೇ, ಟೈಮ್ ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಅಷ್ಟೇ. ಅದೇನು ಪರವಾಗಿಲ್ಲ, ಇಷ್ಟವರೆಗೆ ಆಲ್ಮೋಸ್ಟ್ ಎಲ್ಲ ಆಗಿದೆ. Yeah, I'll stop. That's fine. Okay, once you feel it's good, great. When I'm tired also, I'll stop. It's also this. Let's see. Okay, next. Yeah. Now let us see the temperature profile as well as or I would like you to see the pages 487 and 488 in our Cengel and Bowles. You refer page 487 and 488 in Cengel and Bowles. Very good, this one. So, not Cengel and Bowles. This is Cengel and Gajar. I'm sorry. Cengel and Bowles is for the other one. This is Gajar. Okay. Afshin Gajar. Afshin Gajar is from which place he is from? Oklahoma State University, Stillwater. Okay. And Yunus Angel is University of Nevada. Both are Iranians actually. Nevada or Nevada, I don't know. Nevada. Nevada is a desert, so he's there. So he understands heat transfer better. So he's written that book. What you experience, huh? Carrot, how? No, he's not Ghajar. It is Ghajar. Eh, Ghajar. Eh, Hindi it is Gajar. This is Ghajar. Okay. So Mahaprana. Okay. Mahaprana and Alpaprana. It's very important, students, how you use Mahaprana and Alpaprana, because if you say Phala, Phala means what? Fruit. Correct? No, Phala means fruit. Phala means meat. If you say instead of Phalahara, you say Palahara, it means meat, meat eatable. Okay? And if you say Phalahara, it means fruit eatable. So anyhow, so no small difference. There is no fur there. There is no fur in Indian languages. It is no, not phala. Don't say phala. It is phala. Phala. Per. It's not per. ನಿಮಗೆ ಫಲ ಅಂತ ಕಲಿಸಿದ್ರ ಪ ಇಲ್ಲ ಯಾರು ಹೇಳಿದ್ದು ಪ ಇಟ್ ಇಸ್ ಪ ಅಂಡ್ ದೆನ್ ಪ ಅದು ನಿಮ್ಮ ಮಿಸ್ಟೇಕ್ ಪ ಇಲ್ವೇ ಇಲ್ಲ ಹಿಂದಿಯಲ್ಲಿ ಅದಕ್ಕೆ ದಟ್ ಇಸ್ ದ ರೀಸನ್ ಅವರ್ Iranians used to put something like this to say it is fur. Pal. Pal is not the case. Pal is not Indian at all. We always say pal. Pal. Phala. Phalavastu. Phalavastu. Phalavastu alladu. Phalavastu. Because we can get back by the way we tell. You see the way we say ka ka ga ga na, where your this touches, you see. It's all Vargiya Vyanjana, which has been Vargiya means that can be classified. Classifiable consonants. Swaras, vowels. Classifiable consonants. Ta ka ga ga nga, cha cha ja ja nya, ta ta da da na, ta ta da da na, pa pa bha bha ma. Just see your where the tongue touches. So nice, is it not? Then which cannot be classified? Avargiya Vyanjana. What are those? Yara, la, va, sha, sa, sha, ha, la. Which cannot be classified. Unclassifiable. Such a nice thing, is it not? Chalo. Now, this you have to refer for what? For Nusselt number in the. Okay. See, for a. Generally, what happens, the in terms of heat transfer, we generally say the governing equation, the governing equation, the governing equation for heat transfer in circular duct, okay, is given by this. You have to, derivation is there, you can see it later. Okay, u dou t by dou x, which means x in the direction of the pipe. If this is a pipe like this, circular pipe, okay, this is the circular pipe, this is the x direction. and this is the R direction. Okay, this R here you get is equal to alpha by R into dou by dou R into R dou T by dou R. This is the governing equation of pipe flow. Change in temperature in the x direction is equal to whatever the heat is diffusing in the R direction. This is the way the heat transfer happens in pipe flows. You can consider Z. This, instead of X, you can consider Z. It's cylindrical heat transfer or heat transfer in cylindrical coordinates. Heat energy equation in cylindrical coordinates. Through that you get that. Okay. Anyhow. Now, if for a constant heat flux or constant heat flux condition, heat flux condition for constant heat flux condition, we can get at the end after the derivation is done, we get since what is this here? You get dTm by dx is equal to 2 uh, dtx by dx is equal to, okay, if I write here, I'll write it here. For a pipe flow, we know that dTm by dx is equal to dTm by dx for constant heat flux is equal to q dot s, correct, into p, which is area, divided by m dot cp into x, correct. Now this for circular pipes, for circular pipes, p is what, perimeter is what, perimeter for circular pipe is given as 2 pi r, correct. And what is the, yeah, 2 pi r, okay, 2 pi r is the perimeter, right. And then when you put that into area, what is m dot cp? M dot can be equal to, m dot can be equal to rho v average, v average into a cross section, which is equal to rho v average into pi r square. What happened?
You got U there, U dT by
U is because you are taking u in this direction. Otherwise, you will take this one as what, in take it in the take it in cylindrical coordinates. If you consider heat transfer equation in the cylindrical coordinates,
there we get 1 by alpha dou T by dou T.
just a second. This is not in cylindrical coordinates. This is in which coordinate? Cartesian coordinates. Now in the cylindrical coordinates, you have to write this. So what happens here? Instead of x, you get r. Here, this would not be, this w will be u here. Z will be x here. Okay. It is better if I write it w here so that you will not have confusion. I could have written here w. Instead of this, I could have written here w into dou t by dou z. That would get get away the confusion. But anyhow, don't worry. You can convert that z and u and all those things. It's cylindrical coordinates. Is it not? So we can have using this we can have pi r square. We can have totally as, okay, this one when we apply, we get dtm by dx is equal to q dot, here 2 is there, okay, 2 q dot s, q dot s is q dot w, I'm sorry, we use q dot w, is it not, q dot w divided by rho v average into cp into r. This is dou tm by dou x. Write this down to you. And then the Nusselt number comes for constant heat flux. because Nusselt number is important, is it not? Done. Done. Okay. Next for constant heat flux or constant heat flux or constant heat flux condition in circular tubes, very important. In circular tubes, Nusselt number is equal to HD by K, always equal to 4.36. Done. H does not change. H does not change when it's fully developed flow. Okay, for fully developed flow, very important. For fully developed flow, thermally as well as hydrodynamic, both. There should not be variation in hydrodynamic as well as thermal. Next, for constant surface temperature, you can write NUD. Okay, we will have NUD. Okay. For constant surface temperature condition in circular tubes, we have NUD is equal to HD by K, comes as 3.66. Remember this equation. Circular tube 4.66 constant heat flux, more heat transfer. In constant surface temperature, less heat transfer, it comes to 3.66. This derivation has been done. This derivation requires a lot of iterations. So this is not done in Senjal. For this you can refer Senjal. Ili? dx. ಇದು x ಅಲ್ಲ, ಐ ಆಮ್ ಸಾರಿ, dx. ಇದು ಕೂಡ dx. ಸರಿಯಾ ಅಲ್ವಾ? ಸರಿ, x ಇಲ್ಲ, ಪೆರಿಮೀಟರ್ ಮಾತ್ರ ಇದೆ. ಸರಿಯಾ? ಕರೆಕ್ಟ್ ಅಲ್ವಾ? ನೆಕ್ಸ್ಟ್ ಇದನ್ನು ಬರೆದ್ಬಿಡಿ. ಆಯ್ತು, ಇಲ್ಲಿಗೆ ಕನ್ವೆಕ್ಷನ್ ಹೀಟ್ ಟ್ರಾನ್ಸ್ಫರ್ ಆಯ್ತು. Then also refer page number 489. Refer page 489 in Senjal and Ghajar. Senjal and Ghajar for Nusselt number for different cross sections of ducts. ಏನಾಗುತ್ತೆ ಅಲ್ಲಿ ಕೊಟ್ಟಿದ್ದಾರೆ ನೋಡಿ. ಈಗ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ rectangle, when it is A by B ratio is 1, then it is 2.98. Nusselt number for a what is a square cross section, it is 2.98. When it is a rectangular cross section with the one side twice as other, it is 3.39. And when it goes to infinity, very circular tube, very infinite, sorry, a very thin plate difference, it goes to 7.54 Nusselt number. That's it, not more than that. So maximum Nusselt number we can have in a rectangular, this one can be 7.54, not more than that. Okay, and then that is for constant temperature heat flux, constant temperature and heat flux 8.24, till there it can go. So it depends. Okay, so and then isosceles triangles, ellipse, different conditions are there. So maximum is for rectangular duct with simple slide. Okay, a small gap. For that there is a maximum Nusselt number, which means highest heat transfer coefficient. Whereas highest heat transfer coefficient. Makes sense? Chalo, done. So, any doubts, students? Can we do problems? We'll do problems. One or two problems are there here. So, चलो करते हैं. One more question, because I can start with the um, our this one, but there is less time, 20 minutes. So I don't want to start with natural convection. We will do one or two problems which have come in gate on this. Okay. Okay. There have been quite a number of questions. Ah, 2020. We'll go 2020 directly. Let us go to 2020 gate. Uh, Gate IITK. Okay, download info. So let us go with 2020 mechanical engineering, and in that let us say water weather flows. Control F, flow. Flow. No, we don't get any flow. Okay, so we'll go to set 2. Maybe it's somewhere here, session 2. So water flows for 2 marks. So for 2 marks, water flows, water flows, water flows, water flows. So water flows. So where does water flow? Water flows. Water flows. Yes, water flows. Observe this water flow. Do this question. It's not very difficult. So keep. In I3, Mr. Agastya, you have something to say? Say it to me. Yeah. That's the question. First question always takes time. Second, third question becomes easy. Constant heat flux. think we can apply some equations directly and get the answer. See the depth which we have gone. Actually, we have gone too much depth without a notice. Whatever, is it not? This has come from 2020 set 2. Okay. See that 2020 ME set 2. Banta, not done yet. Okay, have you written the question or you understood the question? Is it not? Don't have to write it again. Don't you apply this equation? Where is this? This equation. You get m dot cp. Oh, sorry. The volt is constant volt. No. You cannot. I'm sorry. Okay. It's constant, so constant flux. Can't you apply this one? You can directly apply this and get the answer.
We need wall temperature.
Wall temperature is given, right? Wall temperature is not required. Where it is required here?
So we have to control.
We have to wall. Yes, yes, yes. You can find out the mean temperature. Mean temperature is given. You have to calculate the wall temperature. Yes, do it, do it. You have to find out Q dot. Once you find out Q dot, you can find out always. Is it not? H is known. Yes or no? So once H is known, you can calculate H here, right? H varies. No, H means constant. So once you know H, you have to calculate what is delta T. Delta T is known. Sorry, T mean is known at the exit. Q dot is known because H is known. Or Q dot W, constant heat flux Q dot W is known. So once Q dot W is known, Q dot W is equal to H into delta T. Like that. Here T mean at the exit and T inlet is known, P is known, X is known, M dot Cp is known. No, 85. Let us do it. So what is it required? So one of the things, okay, I'll give you some time now, do it. First one, you go wrong, there's no problem. Online students got the answer? You can write T of uh, E is equal to Ti plus Q dot S A surface divided by M dot Cp. Te is given as 70, Pi is equal to given as 10 plus Q dot S we do not know. As, okay, it is yeah, As is known, which is uh, 2 times, or we can write 2 pi r. R is given 3 centimeters, so 1.5. So pi d. So you can write pi into 0.03 into, we can have length is 20 meters is given. So 20 meters, okay. M dot Cp. What is M dot there? M dot is 720 kg per hour. Cp is given 4.179. So you can find out Q dot S, right? What did you get the Q dot S or Q dot W? We use Q dot W. Is it not? Q dot W, AW. What is Q dot W? What is Q dot W? Once you get Q dot W, here from this you can find the H also, is it not? How do you find out the H? H is nothing but M dot Cp, is it not? Why? Because heat transfer is equal to the this one. You see that? Is it not? So Q dot W can be equal to, or Q dot, okay, or you can write yeah, Q dot is equal to Q dot wall into area of wall is equal to m dot Cp into T exit minus T inlet, right? That is of course, yes. But we have to find out the wall, is it not? So Q dot W is known, right? So we have to find out H, right? How to find out H? H is given? Okay, H is given. Fine, then that's fine. Then you get Q. What is Q dot W you got? What is that you got? 1 1. What's the answer? Q dot W. 26,000. It's not correct. Okay, let's see what's. Do it and tell me what is correct properly. Get Q dot W. Once you get Q dot W, Q dot W is equal to H into kg per hour. I'm sorry, 720 is kg per hour. So you have to multiply by 3,600. Make the correction properly. 26,000. Q dot is 26 kilowatt. Right. So this is so Q dot W is equal to 26.6 kilo. Right. So 26.6 into 10 power 3 is equal to H, which is given as 1697 into delta T. Delta T is, to get the answer, T wall minus TE. Right. T wall minus T. So T wall, you get it as 85.7. Right. Round off to one decimal place. Have you rounded off to one decimal? Or you have truncated? 85.6? 67, then 67. You have to round off to one decimal. Be careful on writing that. Because they might give without any this one. When you round it off, no, then it may so happen that you will get only 85.7. If the range is from 85.65 to 85.69, they will easily say round off to one decimal, and in the answer they will give only as 85.7. So if you write 85.6, you are gone. You did not read this. You have to read that and write it properly. Otherwise, you'll get a wrong answer. Okay. Then you will say, sir, I've got the right answer, but still I did not get this one. They will concentrate on this.
In case we write an extra digit number,
You must not. You must not. Not you cannot. I don't know whether you can or not. If there's round off to one decimal, I think only one decimal you can add there. You cannot add two decimals there. So don't write 85.6. That's the wrong answer. You have to write 85.7 only. No, it's not always the case, but if they do it strictly, you cannot question. 85.7 or range we can say.
The range will be usually plus or minus.
Yeah, usually the case, but not always. You cannot say. Okay. So question number is 51, is it not? Question number 51 here, 85.1 to 86.1. So you are saved. What did we get? 85.7, right? So in that range, anything is right. But in case, be careful. I'm not saying that it will come, but I am asking you to be careful. That's it. Okay. So what's the time now? Yeah, 5 6. We'll stop it here. Okay. We'll continue with more problems in the evening. Okay. Sure.